record, and let's go to the whiteboard. Okay, yeah, let me go through that. Okay, so Valeria, we have an in-person lab on Thursday, but that's still experiment 7 on the calorimetry. So I think you already did calorimetry last week, so you don't have another in-person lab this coming week. That's for the second group to do experiment 7. Okay, then after that, next week, we'll have another experiment. Does that help? Okay, I've been trying to work on those modules 8, 9, and 10, and I hope they aren't. I try to make sure they were done before I published them. There is, though, if you just know, for this week, in terms of not in-person lab, but it's going to be an online lab. So the experiment 9 is an online lab. You're just going to observe what's in the PowerPoint to get your values for your lab. So experiment 9 is not in person. It's going to be online. And then next week for the periodic table, that's a simulation. Okay, so next week we have an in-person lab, that's experiment 13, and then we also have a simulation. Does that help explain what's happening? So you're having both two things, an in-person lab, and then you have your online lab. All right. I hope that explains your confusion. Does that make more sense now? So what you're seeing is for this week, you're going to be doing the online lab and not the in-person lab because you already did that. Good morning, Leslie. Okay, so basically, I've been trying to get the videos done. I have the redox done. There were just a couple things about the redox, a couple terms that I didn't get a chance to do. Gosh, I hope the video sounds okay because I think I had a bunch of interruptions. So basically, I'll put that up, and then basically all of chapter 5 is done, but we'll go through a little bit today as well. I just want to make sure. Sorry for the duplication. Your exam, normally I want us to do it in class, but I hate to tell you this, we're running a little behind or a lot behind. So what we're going to do is I have it scheduled for next week on the 22nd on Friday, because we're doing our exams on Fridays. But instead of having you do it in class, I'm just going to have it available and anytime that weekend, starting Friday after class till Sunday, you can take the exam. So it'll be due Sunday at midnight. So make sure you take your exam like no later than 10 o'clock at night on Sunday. So you'll have a weekend to schedule yourself, Friday and the weekend to schedule yourself. So for those of you who work on the weekend, then hopefully you can take it Friday. Those who work on Friday, like right after class, hopefully you'll have some time to schedule to take the exam over the weekend. Okay, so that's how I'm going to run exam 2, just because unfortunately I'm talking too much. I think I spent too much time on chapters 1 and 2 with the conversions and the nomenclature. So unfortunately we're going to have to speed up a little here. Okay, so basically we finished 4. We're going to finish 5 today and start 7. We are meeting in person this Thursday in lab. So there is experiment 7 this Thursday. I think the only time we're not meeting in lab would be that the first time we won't meet in lab is going to be in November. Okay, so I just wanted you to be aware of what to anticipate next week, because if I tell you like on Thursday, oh, tomorrow's your exam, it's not quite fair. So I just want to make sure we have enough time to go through the material and you have time to study it. So yeah, it will be, no, you cannot work through it throughout the weekend. It will be 2 hours. So once you open it, you have 2 hours to complete it. So it'll be like last time, except it's not scheduled for class time, only because I want to use that time to lecture and make sure we're get back on track. Okay, so Does that, so basically this one is 2 hours. So it is timed. It's not something you can come in and out of. Okay, again, it's open, no open book, but it will be like the last exam. So it will be tight for time, just so you're aware. And you will need to upload your work. Okay. And that's just what I wanted to make sure. So the last of the videos will be up. I already recorded them. I'm hoping the last one on Redox. I'm just hoping you don't get too many interruptions. So let's start off with reviewing 5 and going through. On Friday, is the 22nd. So this week I have it on the 22nd. Is that in 2 weeks? Okay. Yeah, it's the 22nd that I'm going to have it. That should give me time to cover everything. Okay. So yes. Did I say, so I thought it was next Friday. So in 2 weeks, it will be the 22nd. Okay. That's probably why I'm so behind. I can never keep track of my calendar, even though I have several ones in front of me, but the 22nd. All right. Okay. And as far as the labs, we're still doing the in-person labs, and we're still doing basically oh my gosh, the best calling. Okay. So we're still doing the in-person lab. And then you also have some simulations and online labs to complete. Okay. All right. Is that clear now what's happening on your schedule? Okay. All right. Sorry, if you have a question, speak up. Okay. Thank you, Octavia. All right. So let's go through. Oh, I have it wrong here. Put this here. Okay. So let's go through then and let's finish chapter 5 and start 7. So with 5, let me ask you this. I'm going to give you a series of compounds. Let's start off with that's a good one. What's another good one? That's another good one. Let's do wow. You would think that I would have more on top of my head, huh? That's a good one. Let's do I think that's a good one. Let's do 2 more. That's a nice one. Let's do let's do oh, we already used let's do this one. That's a good one. Let's do this one. Okay. So all I want to know is you tell me if the compound is soluble or insoluble in water, knowing our solubility rules. So the first one, iron 3 carbonate, soluble or insoluble? Would it be soluble? Actually, it would be, what do you guys think? It's a carbonate.
It's insoluble.
It's insoluble, right? Because it's a carbonate. Okay. And if you look at your cation, It's not one of those ones that have no exceptions, like the ammonium ion or your group 1A metal cations. What about the second one, the ammonium chromate?
Soluble?
Absolutely. And that's because of the ammonium. Once you see that you have this cation, you know it's going to be soluble. I agree. What about silver chloride?
Insoluble.
It's insoluble. Exactly. Turns out the halides like chloride, bromide, and iodide are mostly soluble except when it's paired with silver ion, mercury 1, and lead 2. Okay, let's keep going. You guys are doing great.
Soluble?
Soluble. Sulfates are mostly soluble except when paired with what? What about this one up here?
Insoluble?
It's insoluble. So except when paired with barium ion, calcium ion, slightly soluble, strontium ion, silver, and lead 2, right? Okay, what about manganese 2 hydroxide? Actually, did you say insoluble for the barium sulfate or the manganese 2 hydroxide? Ah, okay. Sorry. I look like, oh, okay. I just want to make sure. Okay, so for the manganese 2 hydroxide, what do you know?
Soluble?
Well, what do you know about hydroxides? Hydroxides are mostly insoluble, right? So this is going to be one of those cases where it's mostly insoluble. You have some exceptions. The exceptions would be like your barium ion, your calcium, and your strontium ion. That's slightly soluble. And then of course the ammonium and the group 1A cations, metal cations. Okay. And what do you know then about, given that, what do you know then about zinc sulfide? Soluble or insoluble?
Insoluble?
It's insoluble because sulfides basically have the same type of rules as your hydroxide. Okay. Now, typically though, let me just, I'm going to throw this out, but if you're going to say, is this a general trend? This is probably applicable, I say with a much lower percentage, like 60% of the time. If you think about, and I don't know where I came up with that number, I just made it up. But like when we talk about ionic compounds being metal, non-metal, in this case, this is a little bit less reliable because you already see exceptions like in hydroxide. But if you think about Coulomb's law, then the force of attraction between your ions is going to be related to the relative charges, or related to the charges actually, divided by R squared. So the stronger the charges, the stronger the attraction, or the larger the charges, the stronger the attraction. So, like I say, it's not perfect, okay? But this is what you can, if I just threw this one out at you. Oh, let's do let's say gold 3 arsenic. Okay. What is the likelihood of it being soluble or insoluble. So what are you more likely to guess? Now you want to educate a guess, but what would you guess for gold 3 arsenate? Is it likely to be soluble or insoluble? And how would you answer that? How would you go about assessing this to find out whether or not you think it's going to be soluble or insoluble? What's the charge on your gold cation?
Two.
That's a good guess. But
Three.
gold can only be a +1 or +3, right? So, or +3. So let's take a look. Arsenate. Where is arsenic? What column is arsenic in? What family is it in? 5. Okay. So basically, if you look at arsenic, what element is it below?
Phosphorus.
Phosphorus. Okay, so let's go through and take a look at this. If it's below phosphorus, then if you had PO4, what's the charge on that? What's the charge on a PO4 anion?
3 minus.
3 minus. So what do you think the charge is on ASO4? Three minus, same family, so it will have similar types of behaviors, right? And that's why we knew about iodate. When we teach you chlorate, you can use it for iodate, you can use it for bromate. So here is, this is phosphate, this is arsenate, okay? So if this is arsenate, then knowing that gold could either be a +1 or a +3, which one will make sense given this formula? It's a +3, okay? So now let me ask you, knowing this is a +3 and a -3, is the force of attraction between my cation and anion really strong? The ionic compound is neutral. Let's compare it to something like sodium chloride. If I just put a +1 and a -1 here, then let's just say the force of attraction is proportional to 1 times 1, right? Oops. It's like erasing. Okay. So let's say K times a +1 -1 over R squared. Okay. Now what we're going to do is we're going to assume K and R are the same. And now let's take a look at the force of attraction between my gold 3 ion and arsenate. So the force of attraction between those two are, it's a +3 times a -3 over R squared. So which is stronger, the attraction here or the attraction with sodium chloride? which has a stronger force of attraction? Sodium chloride or gold 3 arsenate? The gold 3 arsenate, right? This is 9 times stronger than sodium chloride, right? And in most cases, have you noticed we don't have charges that are a +4 or a -4? This is like the maximum relative charges that you can have on your ions. So knowing that how much stronger that force of attraction is in water, do you think it's more likely to be soluble or insoluble?
Soluble.
Well, soluble, just so you know, what does that mean? That means that my gold 3 prefers to be in solution, surrounded by waters, than next to each other. Right? Do you
Yeah.
see that? Okay. So what's happening is this. Suppose I had 2 small magnets. Well, they could be strong, right? 2 weak magnets and 2 strong magnets. Which is easier to pull apart? So is it easier for water to pull apart the 2 weak magnets or the 2 strong magnets?
The 2 weak magnets.
Okay, so when you put sodium chloride in water, right, it's more likely to dissolve, right? Isn't this more likely to be soluble? Now, the 2 strong magnets, do you think they're going to come apart?
No.
So in that case, then your gold 3 arsenate is more likely to be what?
Insoluble.
Insoluble. So because the water can't pull them apart. Does that make more sense?
Yeah, that makes a lot more sense. Thank you.
Okay. Well, I'm not, I wasn't trying to, if you thought I was trying to pick on you because you were answering, I wasn't. It's because when I gave you all those solubility rules, okay, I just like, here, memorize this. But the fact is, if you look at it, you do have a lot of exceptions. That's why I said 60% of the time instead of like ionic compounds or metal nonmetals. But the bottom line, when we look at that, is that the weaker, the smaller charges tend to be more soluble than those with the larger charges. That's why when you look at phosphate, unless it's with the group 1A metal cations or ammonium, they're all insoluble. And that's because it has such a high charge. Where you start seeing the variability is your sulfate and your carbonate, right? Carbonate, I can explain. Sulfate, I can't, but I think that has a lot to do with your R, okay? So when we start seeing some of these exceptions, that's where we have to be careful. But if you have something that you don't quite know, then you can use Coulomb's law to help you make an educated guess. Because the bottom line is what is happening when we talk about salvation. Water comes in and surrounds your anion or your cation. And so they're no longer attracted to their partner. But in this case, there's such a strong attraction. They don't care that water is present. They have a much stronger attraction to each other. Does that make more sense now? So if you're wondering, why are we doing all this solubility, just memorizing it? There's a lot of experimental aspects to it, but also be aware that there is an underlying reason for the way they behave the way they do. Okay,
Wait, I have a question.
sure.
What did it say after larger the charges, stronger the...
Attraction.
Okay, thank you.
You're welcome. Okay, so now let's move on. We're just going to talk about all these different reactions. Precipitation reactions basically what you're doing is making a solid. That's your precipitate. Okay. So all of these reactions tend to be double displacement. So let's go through and figure out how you do these. And what's nice for me is I don't have to tell you much. I can just give you your reactants. So let's say you mix a solution of, oh, what do I want to mix? Oh, that's kind of cute. Oh, would you know that one? Okay, so let's go ahead and mix iron 3 chloride with a solution of ammonium hydroxide. Okay, so you want to complete and balance the reaction. Okay, so this is what you do. You have iron 3 chloride. Okay, we know it's aqueous because it's in a solution, plus ammonium hydroxide. Again, that's aqueous. Okay, so what are the possible products that we can have in order to complete this reaction? Okay, so we have to come up with the products and then determine if a reaction really occurs. So when we come up with the products, there are two ways we can do this. Let me show you the way I typically learned it. Oh, this is, I won't tell you how long ago. I write out my cation, my anion, and I write out my cation and my anion. Okay, and then I think I just like crisscrossing, that's all. Okay, crisscrossing. So my iron 3 will react with my hydroxide, but to make it neutral, I need 3 hydroxides. Okay, so when I do my crisscross, I'm not interested in getting the neutral compound. I just want to know when I mix and match them. And then I have ammonium chloride, and that's nice and neutral. Now, when I do this, cation with cation cannot do, they repel. So you can never have the iron 3 with the ammonium because they're both cations. Likewise, you cannot have anions with anions. They repel. So the only option is you have to crisscross. If I went straight across, I'm going to get back my starting material. Okay, so once you write down what your products are, these are new substances. Okay. Then I have to go through and say, all right, so iron 3 hydroxide, is that soluble or insoluble?
Insoluble?
It's insoluble. And ammonium chloride, what is that? Soluble or insoluble?
Soluble?
It's soluble. So now, because we have something that we've formed, basically we formed a solid, we can have a reaction. Okay, so I have a solid here plus ammonium chloride. That's aqueous because it's soluble. So now all we have to do is balance this thing. I have what, a 3 here, so I need a 3 there. And I need a 3 here. Okay, so far so good. Okay, so let me give you another one. So now that you saw how we do this, right? So first we're gonna come up with our possible new products. And then if I see that there's something new here, like a solid, that's a precipitation reaction, we can complete it. What happens if I give you this? we mix aqueous, say sodium chloride with, oops, with a solution of nitric acid. Okay, so in this case, when we complete and balance, okay, and balance the equation, okay, so we have our aqueous sodium chloride and we have our nitric acid. Okay, so what are my, oops, that's an A in front of there, AQ, all right? So what are my possible products? So I write down my cations. Okay, and my possible products will then be sodium nitrate and HCl. Well, hydrochloric acid always is aqueous, hence it's an acid. Sodium nitrate, is that soluble or insoluble?
Soluble?
Yeah, because both sodium and the nitrate ions. Okay. Now, both of them are completely soluble. So we really don't have a change, and they're both really strong electrolytes. So once they go in solution, they're just going to float around. And if you look, since it's aqueous and it doesn't decompose or anything, nothing happens. So this is a no reaction. Okay, and you can tell, first take a look, aqueous and aqueous. It's like, oh, okay. And then you take a look, it's like there's no possible decomposition. And I'll show you what those look like in a moment. Okay, when we get to gas formation. So that's not going to happen. And they're both strong electrolytes. So you're not going to write anything down in its molecular form. So once it goes in solution, it's no reaction. And then you're done. You don't even need to balance it because there's nothing to balance. Okay, so far so good?
Yes.
Okay, so now let's go through and let's talk about your molecular, what we have been writing, your total ionic and your net ionic. Okay, so when we do a double displacement, everything that you've been seeing us write has been in the molecular form. We're writing out the molecules, we're writing out the formula units, but it's all molecular. Total ionic, this tells you anything that will dissolve and form ions, you're going to write it out. Okay, so it's kind of like if here's my beaker and I have sodium chloride in solution, you're not going to get the molecular form of sodium chloride floating around in your water. You're going to get your component ions, right? The sodium ion and the chloride ion. That's what you actually can see in solution. And net ionic, this is what, these are the players in the reaction. Okay, so let's go ahead and do one set. So I want you to write the molecular total and net ionic equations for when you mix a solution of copper 2 nitrate with sorry, I'm just thinking. A solution of let's just do sodium phosphate. Okay, so what is the reaction? I'm going to write down for my molecular reaction. What do you want me to write? Okay.
Copper 2 nitrate
Mm-hmm.
plus NaPO4, the sodium phosphate.
Okay, it's just like this.
Is it gonna have a 3- charge?
Yeah, so a phosphate has a 3- charge. What's the charge on a sodium ion?
-1 or +1?
Yeah. Okay, so what's the formula for sodium phosphate?
Is it Na3?
Uh-huh. Beautiful. Okay, so what are my possible products now?
Copper phosphate. Wait. Is that right?
Yeah, almost copper what? What's the charge on the copper?
Copper 2 phosphate.
Okay. So tell me what the formula is.
So it would be sorry, let me write it down.
It's okay. Scratch
I'm having
paper
so
is
much
good.
confidence
No,
for you, I'm
no,
sorry.
there's no reason for you to apologize. I just want you to know, scratch paper is good in chemistry. I'm so sorry for the trees, but it's important and very good.
Is it copper 3 and then phosphate 2?
Mm-hmm. And what's my other product?
Sodium nitrate?
Yep. Great. Okay. So I told you I like to do the crisscross. So I would do, well, the way I wrote it here, it's not crisscrossing, but basically I would crisscross it. There's another way I've seen people do, and that's because of the way we generally write our equations with the AB plus CD goes to AD plus CB. So they say, oh, outside, inside. Okay. Always make sure your cation is always written first. So I don't care so much about the order having to be AD, CB or CB plus AD, but when you write your molecular formula, always write your cation first for an ionic compound. Now that I'm done talking, you've had a chance to go through your solubility work. So the copper 2 phosphate, what's the solubility? Soluble or insoluble?
Insoluble?
It's insoluble. So when we write the physical state, we say it's a solid. What about sodium nitrate? Soluble or insoluble?
Soluble.
So we write as aqueous because it dissolved in the water. Okay, is this balanced?
No.
Okay, so let's balance it, right? So let's go ahead and put a 3 in front of here. Okay, that means we have 6 here. That means we have 2 here. Is that balanced now?
Yeah.
Okay. And you saw how I got that, right? So when I started, I just said, oh, listen, I've got 3 copper. So I started with the copper first. When I put the 3 here, that meant I had 6 nitrate. So that I had to put a 6 here. That means I had 6 sodium, so I had to put the 2 there. Okay. So far, so good. Now, let's get to the fun part. Okay. So the fun part is this. Let's do our total molecular. Our total ionic. Oh my goodness. And what you have to be careful of when you do the total ionic is which subscripts become coefficients and which subscripts stay. So like in this case, this is a strong electrolyte. It's ionic and it's soluble. So when I have a strong electrolyte, okay, then I have the 3 here, which tells me that's my coefficient. I have 3 copper 2 ions floating in solution. Okay, but how many nitrates do I have? Well, for one molecule or one formula unit, I have 2 nitrates, but I have 3 of them. So I have a total of 6 nitrates. So be aware, this 3 is part of my nitrate, but this 2 and this 3 become part of your coefficient. Okay, here again, I have an ionic compound and it's soluble. So therefore it's a strong electrolyte. So we're going to take it apart to its component ions. Sodium ion in one formula unit, I have 3 sodium ions. Since I have 2 formula units, I have a total of 6 sodium ions. Okay, and this coefficient applies to both cation and anion. I have 2 phosphates. Okay. Now let's go to the product side. Anything that's not soluble, okay, you can just copy straight down. So the only thing you take apart for your total ionic is anything that's soluble and a strong electrolyte. Everything else you just carry down. Here, sodium nitrate, it's soluble and ionic compounds are strong electrolytes. So this is ionic and soluble. We're going to have to take it apart. You get 6 sodium ions plus 6 nitrate ions. Okay, so if you're going to tell me that total ionic equations take a lot of space, they do. Okay, so your whole goal is to, once you get to this part, after you've predicted your use your solubility rules to predict your products in a precipitation reaction, then you use all your rules about what are strong electrolytes to do your total ionic. Okay. Now that you've done that, oh my goodness. Well, let's go through the terms once more and then we can move on. And then also in the video, I've done a bunch of calculations with your net and your total ionic equations. So that's worthwhile seeing because that's also in your study assignment. And those are so much fun. I think you'll like them. Maybe. They're fun. They're fun. A lot of work, but fun. Okay, now, while I'm talking and you're admiring this huge total ionic equation you come up with, which are my spectator ions? Now remember, what are spectator ions? Spectator ions are the ones that are just floating around in solution. You've got some ions.
The sodium and the nitrate.
Yes, because they look exactly the same. If they're not exactly the same, then okay. Do you need to have the same coefficient? I've never seen it where we had different coefficients. Okay, nitrate, no change. Sodium ion, no change. These are your spectators. They go in solution, they sit around and watch everything, but they don't participate in the reaction. So when you remove the spectator ions, then you get what we call the net ionic. These are the actual players. These are what react, get you your new product. So I didn't box the copper 2. Box, I didn't box my phosphate. And my solid has to come down. Okay. And that's your net ionic equation. So what happens is this, you can have a lot of other things in solution that are reacting, but your copper will react with your phosphate to form a solid. Okay, your copper 2 ion. So basically the whole thing is that it doesn't matter what your anion is when you make that solution. It doesn't matter your cation. But when they actually are in solution as ions, they're going to react. Okay, so those are your molecular total and net ionic equations. So let's have you do one. What is the net ionic equation for the reaction that occurs when aqueous sodium chloride is mixed with a solution let's see, lead to nitrate. Okay, so what do I write? NaCl. Okay, thanks, Aisha. So will you want to do the molecular first? It's kind of easier to do the molecular and do the whole trend to get to the net ionic. I agree. All right, sodium chloride plus.
Would it be PbNO3 too?
PbNO3 2.
Yes.
Yeah.
Aqueous. Yes.
Okay. What are my products?
Would it be PbCl2?
Right. So outside and inside.
Sodium.
So Pb, since that's a +2, we need 2 chlorides. And what's my,
the 2 chloride.
and that would be what one?
Is it solid?
Solid. And then my other product will be
Sodium nitrate?
sodium nitrate. And my state will be
Aqueous?
aqueous. Okay, so let's balance it, right? What do I need?
You need a 2 in front of the sodium chloride.
I think so. And you need a 2 where else? Yep,
and the sodium nitrate.
perfect. Okay. So now that we have that done, you want to do the total ionic before we get to the net ionic? It's very sequential, right? So this is an ionic compound. It's soluble, so it's a strong electrolyte. We have to take it apart. Okay, this again, ionic compound is soluble, so it's a strong electrolyte, so we have to take it apart. Okay, here it's a solid, so I'm just going to copy it down. Salt, soluble, strong electrolyte, so we're going to take it apart. Okay, now, what are my spectator ions?
The sodium and the nitrate.
The sodium and the nitrate. Okay, now that we've done that, we can remove their spectator ions and write our net ionic equation. And what does that look like? So we're getting rid of this sodium ion, right? Because that's a spectator. I agree, Aisha. So what about the chloride? Do I write the chloride down?
Yes.
Ye-
Yeah? What else? Keep going.
Plus
The
lead
lead too.
Uh-huh. Keep going.
yields lead chloride.
Uh-huh.
Solid.
Beautiful. You're done. That's it. That's my net ionic equation. Okay, you think you might sit back and relax, but I'm not going to let you yet. Okay, ready? Acids. What's the definition for acids? What happens when you dissolve the acid in water? What does it give you?
Hydrogen.
Yes, a hydrogen ion. Okay. What about the bases that we're looking at? What does it give you when you dissolve it in water?
Hydroxide.
Yes. Yes. Okay, so this is your Arrhenius definition of acids and bases, just so you know. Okay, now when we talk about it, just so you know, when you have an acid and you dissolve it in water, okay, I'll just show it like this. Okay, you're going to form what we call a hydronium ion. Okay, why is this? Oh, you can't see that hydronium ion. So if you see that, this is, we equate this to just H plus instead of writing the whole thing. Because remember, when you're in water, it's very hard to just have an H plus floating around just by itself on its own. Because the oxygens in water all have their lone pair electrons. So it will form a bond to that H plus. And that's a hydronium ion. There's just a network with those, the lone pairs on the oxygens. But normally when we just write it, just to save us time of, writing H2O is just a lot of work, apparently. You'll see us often write it just as the hydrogen ion. Okay. So just, these two are basically the same. All right. So just so you're aware of when we talk about the hydronium ion, what is that? Why is that there? The other thing about acids is that they can give you more than one H plus. And I think we've seen this before when we did our titration. So when we look at something like hydrochloric, this is a monoprotic acid. It just gives you one H plus, one hydrogen ion. And I'm just giving you the terms. So when you hear it, it's not a surprise to you. In sulfuric acid, this is called a diprotic acid. Okay, so polyprotic acids just tells you can get many hydrogen ions. The diprotic acid is specific. You can get 2 H pluses and a sulfate. Okay, and when we did our titration with oxalic acid dihydrate, what kind of acid is oxalic acid? Is it monoprotic, diprotic? How many hydrogens am I getting?
Diprotic?
It's diprotic because I can get 2 hydrogens. And that's why when you take a look at your balanced equation with oxalic acid, we had to have 2 sodium hydroxides for every 1 oxalic acid dihydrate. All right, now, strong acids are strong electrolytes. What are the 7 strong acids I want you to know?
HCl,
Mm-hmm.
hydrogen bromide,
Or hydrobromic acid. Mm-hmm.
hydrochloric acid, sorry,
It's okay.
hydroiodic acid,
Yes.
nitric acid,
Yeah, you're doing great.
sulfuric acid,
Sulfuric acid. 2 more.
I don't remember.
Well,
Sorry.
that's a pretty good start. 5 out of 7. Does anyone want to help Brittany out? Brittany, right?
Yeah.
Okay. Anybody want to help out here? She's got 5 out of 7. You just need 2 more. What's that called? What's that called? Chloric acid and
Perchlorate.
Yep, exactly. So then tell me a little bit about the oxalic acid, since we were talking about that earlier. Is this a strong or a weak acid? How do you know? See this list here that you guys helped Brittany with? Because you got most of them except for the last 2. Is it one of those? Andrea's like, no, I don't see it in there. If it's not one of the 7 strong acids, what kind of acid is it?
Weak acid.
Yep, this is a weak acid. Okay, so if you know your 7 strong acids, then I can throw all these acids out at you and you can tell me if it's a strong or weak acid. Because you know your 7 strong acids. If it's not one of the 7, it's a weak acid. Okay, so what about HF? Strong or weak?
Weak.
Yeah, absolutely. Oh, what about what's in your salad dressing? Acetic acid. Strong or weak?
Weak.
Weak. Beautiful. Okay, now, strong bases are strong electrolytes. What are my strong bases? They're typically your group 1A metal cations with hydroxide. Okay, so sodium hydroxide, potassium hydroxide, cesium hydroxide, okay, etc. Also, limited solubility. And that's why when you guys did your activity series, when you reacted calcium with water, you were forming calcium hydroxide. Your solution was really basic, and you had actually calcium hydroxide. When it's dissolved, is completely dissolved, but it can only go to like 0.2 molar. Okay, so limited solubility. And that would be your calcium hydroxide, barium hydroxide, and strontium hydroxide. Okay, a weak base that you should be aware of, and we're going to be talking about this one a bit more, would be ammonium hydroxide, because it can dissociate to ammonia gas and water, depending upon how basic your solution is. Okay, you can push it one way or push it the other way. So you should know what your strong bases are, and you should know that ammonium hydroxide is a weak base. Now, when we do acid-base neutralization, so typically what we're going to form is water and a salt. And they tend to be give off heat too. So you'll see a temperature increase. So basically, if I gave you hydrochloric acid and sodium hydroxide, okay, so you say, oh, look it, I have an acid. Oh, and I have a base. So you're going to form water and your salt. That's not your salt. Okay, so it's a double displacement again. And in this case, it's already balanced. The other thing is, notice I have a change from aqueous. I'm forming a liquid. So therefore, it's a reaction. You don't write no reaction. A reaction occurs. You're forming a liquid. So when you look at the players, right, the sodium and chloride ions are basically spectator ions. So your net ionic equation is going to be H plus hydroxide goes to water. Okay, so basically for acid-base neutralizations, this is really the crucial net ionic equation that you're interested in. So if I gave you this question, what is the net ionic equation for the neutralization of oxalic acid dihydrate with potassium hydroxide? What would be the net ionic equation? What do you think the net ionic equation is for this? Are you working it out? What do you notice? Oxalic acid, dihydrate, right? Reacting, let's say, with potassium hydroxide. What are you going to form? What do you form when you have a neutralization? An acid, water. And what else?
So
Your salt. Okay, now it's not balanced, right? I get that. What do you think my net ionic equation is? What are the key players?
the hydrogen and the hydroxide ions.
Exactly. So when you have acid-base neutralizations, for the acid-base neutralization, this is going to be your net ionic equation. If you work this all out and balance it, okay? Okay, and these H2Os are not formed from the reaction. They just happen to be locked up in the salt, the solid, right? You'll need a 2 here, you'll form a 2 there, okay? But you get 2 H pluses, hydrogen ions here. So when you get rid of your 2's, because you're going to divide by 2 to get the lowest whole number ratio for your coefficients, anytime you have a hydrogen ion, it will react with 1 hydroxide ion to form water. This is your net ionic equation, okay? In fact, let me give you one more and then we'll move on to gas evolution and redox. If I said you neutralize let's say hydrobromic acid with calcium hydroxide. What is the net ionic equation? What would you tell me?
Hydrogen plus hydroxide yields water.
Yeah. What do you think of that? That wasn't so bad, was it? So when we did our titration, we reached, when you get this, so all of your hydrogen ion and all of your hydroxide ions are used up. Okay, so we're not talking about limiting reactant, it's equivalent, right? That's what we call the equivalence point in a titration. Okay. Everything's neutral. Okay, and that's what we were doing in the beginning of the semester when we were doing our titrations, right? We were looking for that slight change in our phenolphthalein color, so we know we hit equivalence point, and that's because you know it's a one-to-one relationship. That's how we could calculate our concentrations. Any questions about acid-base neutralization? Not so bad. Okay. Gas evolution equations. Okay, so there, these guys I want you to memorize. I want you to memorize a lot of stuff now. Okay, when you form H2S directly, typically you're going to see this as a gas. Okay, that's a gas formation. Why is this? Is some soluble? Yes. Okay, again, very limited solubility. This smells like rotten eggs. Okay, it doesn't take much to get the gas. Really not something that you should be like going around and breathing in much. It's not necessarily the best thing for you, but it smells like rotten eggs. So if I gave you something like sodium sulfide solution plus, let's add, let's go ahead and add a hydrochloric acid solution. Okay, you are going to form hydrogen sulfide directly plus sodium chloride in solution. Okay. All right. So when you form this directly, you'll write gas. Okay. If you form carbonic acid, okay, and you see that it's aqueous, it doesn't mean that there's no reaction. This will decompose to water and carbon dioxide. Okay, so if I gave you, let's say, acetic acid, plus sodium bicarbonate, your baking soda, okay, you will form water, carbon dioxide gas, and sodium acetate. And it's this part. If you originally look and say, oh, listen, everything's aqueous, it's no reaction. Actually, that's not true because this will decompose. Okay, so some of it stays in solution as an acid, but most of it comes apart. It's not that soluble. If you form sulfurous acid, this will decompose to give you water and sulfur dioxide. Okay, again, not the best thing to breathe. So if I gave you something like hydrochloric acid plus sodium sulfite what you're going to get is sodium chloride plus water and sulfur dioxide. Okay. That's my gas evolution. All right. Put a 2 here, put a 2 there. Okay. And the last, if you form ammonium hydroxide, okay, this will decompose to water and ammonia. Okay, and the one thing, unfortunately, I don't have enough time for us to do everyday chemicals, but like smelling salts with the ammonium carbonate. What's going to happen is if you start breathing in the smelling salts, it will decompose and you're getting basically ammonia, okay, coming out. And that's what causes people to wake up from a faint. So if I gave you, let's say, ammonium chloride, and I react it with sodium hydroxide, okay, you will get ammonia gas plus water plus sodium chloride. Okay, so those are your 4 gas evolution reactions that you need to know. All right. All right, so let me just, I know it's 10:45, so let me just introduce you to another type of reaction. These are redox reactions. Okay. And a redox reaction, in there, you're going to see a transfer of electrons from one substance to another. Batteries work on redox reactions. Combustion reactions are redox reactions. We get a lot of energy from redox reactions. So combustion is a redox reaction. When you react a metal with nonmetals, this is a redox reaction. Okay. So there are a lot of different types of redox reaction. Rest formation. Is a redox reaction. So we can have desired redox reactions, we can have undesired redox reactions, but redox reactions are important. So what we'll have to go through next time I see you is this. How do you know it's a redox? And we know this because we calculate oxidation states. So what the first thing we'll do is go through the rules for calculating the oxidation states. And I'll have that up. Actually, the video I made, the only 2 terms I didn't go through in the video was oxidant and reductant. So I'll have one really short video after that, going through those terms. Okay. I give you too many examples, I think. I apologize for being so slow. Let me stop sharing here. Are there any questions? Was that fast enough for you, or did I bore you? Was that too slow?